Hi, welcome to Module 7 of Lecture 6. Now we've gone through talking about extrema, defining them, discussing critical and stationary points, and how they relate to possible minima and maxima. We've done the first order condition and the second order conditions. We're now ready to put them all together and come up with a single method for finding extrema. Before we do that, though, we need to revisit our earlier discussion of global and local extrema. So far, what we've done is look at functions, right, and identify where the stationary points are, which are the points at which the first derivative equals 0. So over here, you can sort of identify one over here, one over here, one over here, and one over here. These are all candidates for local extrema, local minima or local maxima, or potentially inflection points. They're the points at which the function is largest in the region around those points. They are not, however, necessarily global minima or global maxima. Each one of the 4 points on this particular graph, and I'll make that a different color, make it a little more vivid. Each of these 4 axes is a possible local or global, is a local minimum or maximum. What about the global minimum or maximum? Well, you can look by observation of this function. If the domain of the function goes from here to here, it's pretty clear that the global minimum is going to be down here, and the global maximum is way up here. So in fact, none of the 4 local minima or maxima are actually global, is the global minimum or the global maximum. There is only one in this case, global minimum, and only one global maximum in this case. Note that in general, you may have many local minima that actually can have different values. So for instance, this local minimum is actually less than this local minimum. But the only way to get more than one global minimum is for more than one point to have exactly the same value of the function. Same with the global maximum. You can't have more than one global maximum that have different values. So the question is, how do you know if your local minimum or maximum are actually global minimum or maximum? Before we get to that, it's helpful to refer to the extreme value theorem, which says that on any closed and bounded domain, a continuous function achieves its global minimum and its global maximum. So those have well-defined actual values. In particular, it also means that somewhere in the domain is the minimum and the maximum. And we actually have gone through in such a way to reduce drastically the possible places these minima or maxima can occur. In the interior of the domain, so apart from the bounds, the minimum or maximum can only occur at one of the local minima or maxima. So again, inside the domain that the function is defined over, so for instance, if this is A and this is B, and the domain is from A to B, then inside the domain does not include the bounds, and in this region here, the only place we're going to find the global minimum or maximum is at the local minima or maxima. So first we check those possible places. Now the other possible place the global minimum or maximum could occur is at the bounds. So at A or at B. And that's it. So all we have to do to find the global minimum or maximum is to first obtain all the local ones using the techniques we just finished doing in the previous 2 modules, and then evaluate the function at A and B as well, and compare the evaluation of the function at any local minimum or maximum inside the bounds to the evaluation of the function at the bounds. We choose the point that gives you the smallest value of the function for the global minimum and the largest value for the global maximum. And that's it. That's the last thing we need to do in order to actually put forth our entire set of rules. These rules are presented page 168 of this printing. You can see it right here. The list of all rules right over there. To go through them really quickly again. Right. First, you find the derivative. Right. First, you find the derivative of the function. Then you solve the first order condition, which is the set, which gives you the set of all stationary points of the function. There might be one or more x star there, depending on the powers of the derivative. Once you do that, you compute the second order condition. The second order condition at each of these points. If it's negative, you have a local minimum. If it's positive, you have a local maximum. And if it's equal to 0, you must find further derivatives. And I'm not going to write this again on the screen. We talked about this in the previous module, and it's in the book as well. If you take further derivatives until you find your first non-zero derivative. If that first non-zero derivative is a odd derivative, so the third, the fifth, and so on, then it's an inflection point. Then that stationary point you found is an inflection point and is not a minimum or a maximum, and you can discard it. If it's an even derivative, so the fourth, the sixth, and so on, then you treat it the same way you treated the second derivative. And if that first even derivative, that first non-zero even derivative is negative, then you have a local maximum. And if it's positive, you have a local minimum. Once you've gone through and done all this and evaluated all these things, you have a list of potential candidates, potential stationary points that have passed the second order test, potentially passed the higher order test, and you have a list of possible minima or maxima. You want to now evaluate the function itself at each one of these local minima or maxima. Now you want to also evaluate the function at the boundary points. So you have at least two values you have at least two things to compare, and possibly many more things to compare. From this group, from each of the f of x stars and f of a and f of b, the boundaries, you find the smallest value of the function, that's the global minimum, and you find the largest value of the function, that's the global maximum. It might occur at a local minimum or maximum, or it might occur at a global minimum or maximum. Sorry, or it might occur at a boundary point. You will find that by comparing the values of the function directly. And that's it. That's all you have to do. So now let's go through a couple of smaller examples that are unconnected to anything substantive. In the next module, next and final module, we'll go through and look at two examples independently that are more substantively interesting to us. Okay, but first, let's consider these this couple small examples using this technique. Okay, so first, x squared minus 2x plus 1. Okay, here's our function. Put an f there. Okay, first we're going to find the derivative. That's going to equal 2x minus 2. Next, we're going to solve this equation, its first order condition, equals 0. This is going to imply, remember that means implies, that there's only one stationary point, x star equals 1. Next, we're going to calculate the second derivative at this point. There's only one, so we'll just put the 1 in there. Well, the second derivative is just 2. That is always positive. So this is going to be a local minimum. And we don't need to order any other higher order derivatives. So that's great. Okay, so that's so far. Now we're going to compute the value of the function at x star equals 1. Let's see what that is. Well, f is up there, so f of 1 equals 1 minus 2 plus 1 equals 0. So the value of the function at this point is 0. Now, if we had no bounds at all, this would be all we'd have to go by. But we actually have bounds. We can put some bounds in here. Let's say the function is defined from 0 to 5. This is arbitrary. The answer can change depending on the bounds, but this is 0 to 5. Well, then we would plug in 0 here. And 0 gets us 0 minus 0 plus 1 equals 1. 1 is bigger than 0, so this is already bigger than f at 1. So this is not going to be a global minimum. F of 5 gets us 25 minus 10 plus 1 equals 16. Also much bigger than 0, so that's also not a global minimum. So in this case, our local minimum is actually the global minimum. To find the global maximum, we compare the two boundary points because we have no other possible candidates inside. 16 is bigger than 1, so global maximum occurs at x equals 5 and is 16. So we would say that this function has a global minimum at 0, a global minimum at 1, the value of the function there is 0, and a global maximum at 5, at x equals 5. And the value of the function there is 16. So there's one example. Let's do another quick example like we did before. Here's x cubed minus 9x plus 1. Again, f prime is going to be 3x squared minus 9. We will set that equal to 0. We will find that x star can equal plus or minus the square root of 3. That gives us 2 stationary points and 2 candidates for global minimum or maximum. Now we can go through and check this. And check the second order condition at each of the 2 stationary points. So first of all, the second order condition in general is 6x. If x star is positive, that's positive. So at greater than 0, at x star equals the square root of 3. So this is a candidate, this is a local minimum here. And it's less than 0 at x star equals negative the square root of 3. So that could be a local maximum. Note that it's important to evaluate the second derivative at each of the stationary points. They could be different things. They could be minimum or maximum. In this case, we have one local minimum candidate and one local maximum candidate. Now, having done that, we have to go through and figure out what the global minimum and maximum are. Let's again add some bounds to this thing. Let's just add bounds randomly. Say 0 to 10, just because. Sorry, we can't do that. Let's do negative 10 to 10. So those are pretty big bounds. Let's see what happens. Well, in this case, first we'll evaluate the function at the square root of 3 and negative the square root of 3. Well, let's see, the function at the square root of 3 equals 3 square root of 3 minus 9 square root of 3 plus 1. That's negative 6. That's equals 1 minus 6 root 3. That's a negative number. Now we can evaluate the same function at negative square root of 3, and we get negative 3 root 3 plus 9 root 3 plus 1 equals 1 plus 6 root 3. That's a positive number. So far so good. How about the bounds? Well, the function evaluated at negative 10 is equal to negative 1,000 plus 90 plus 1. Right? That is clearly very, very small, much smaller than 1 minus this. So the global minimum is at negative 10. Similarly, this is 1,000 minus 90 plus 1 is much, much greater than 1 plus this. So the global maximum is at 10. Right? So in this case, neither the local minimum nor the local maximum are actually minima or maxima. Are actually global minimum or maxima. So all that calculation actually didn't help us in this case. But this depends on the bounds. If we were instead to change the bounds to negative 2 and 2, and I erased this whole thing because we had no room left, then something different might occur. Remember the function here is x cubed minus 9x plus 1. In that case, f of negative 2 equals negative 8 plus 18 plus 1. That equals 10, 11. F of 2 equals 8 minus 18 plus 1. That equals negative 10, negative 9. Now going back to before, we had the two values of 1 minus 6 root 3 and 1 plus 6 root 3. Now it turns out 6 root 3 is approximately equal to 10.39. So 1 minus 6 root 3 is actually negative 9.4, which is less than negative 9. And 1 plus 6 root 3 is actually 11.39, which is more than 11. So in this case, the global minimum and maximum occur at the local minimum and maximum, plus the square root of 3 and minus the square root of 3. So we see the global minimum and maximum depend on where the bounds are in the shape of the function. The method for finding the local minimum and maximum is always the same as the method we just talked through. Then you compare it to the function at the bounds to see what the global minimum or maximum are. The good news is you don't have to do anything more than that. You calculate the local min and max using the derivatives, and then you compare it to the function at the bounds, and that's it. No other points need to be compared, which saves you a ton of time over actually by hand going through and checking all the different values of the function at every point, if you could even do that. That's it. That is the method of optimizing a function, of maximizing or minimizing a function. In the next and last module for this lecture, we're going to give 2 examples taken from stuff that's commonly seen in political science and also sociology and economics and so on. Thank you very much.